And in chapter 9, we were talking about solutions. And remember, solutions are the things that have the aqueous symbol next to them. And they are made up of two things. They're made up of a solute, which is the smaller part of the solution, and they're made up of a solvent, which is the larger part of the solution. Typically, the solvent's what you dissolve, or the solute's what you dissolve in the solvent. So again, an example, if we had water and we had some sodium chloride salt, the sodium chloride would dissolve in the water and it would make a sodium chloride solution that would get the aqueous symbol. Here, the water would be our solvent and the sodium chloride would be our solute. Again, a reminder that basically the name of the solution is the solute. And remember that water is a really good solvent for things that are ionic and things that are polar. We also talked about the idea of like dissolves like. And that's the idea that if you have something that's ionic, it's going to be good to go with something that's polar. They're going to mix. If you have something that is polar, it's going to be good to go with something else that's polar. If you have something that is nonpolar, that will also be good with something else that is nonpolar. So all those things will be soluble in each other. Insoluble or will not really mix together is really when you cross over. So if you try to take something that is polar and something that is non-polar, those two guys do not mix as they're using very, very different types of intermolecular forces or ways they interact with each other. So over a long period of time, they really don't have a way to maintain that interaction. All right, so where we left off was we talked about a couple of things towards the end there. We talked about equivalents. We also talked about electrolytes as well. And remember, electrolytes are things that basically produce ions in solution. And because they produce those ions, they're able to conduct electricity. Things that are strong electrolytes will 100% break apart into ions in solution. And because of that, they conduct electricity really well because there's a lot of ions in that solution. There's also weak electrolytes, which mainly stay together, but does produce a little bit of ions. So they're still able to conduct electricity, but nowhere near as strong as a strong electrolyte will. A non-electrolyte is something that will dissolve in water, but will not produce any ions. And because there's no production of ions, that means it will not conduct electricity. Any question on that stuff that we talked about before? All right, let us continue on here our journey. We're now going to really talk about some concentration units for solutions. And the first sort of concentration unit is mass percent. It is sometimes abbreviated M/M or percent M/M for mass to mass percent. And to calculate the mass to mass percent, you take the mass of the solute divided by the mass of the solution, and you times it by 100%. Now, the important part of this one, and where you do have to be really careful in these type of problems, is the actual bottom part of the calculation, and that is the mass of the solution. So as we just talked about, the solution is made up of two things. It's made up of the solute and the solvent. And you do want to make sure that you are using the mass of both of those when you do the calculation. The reason I say that is because in a lot of mass percent type problems, they very commonly will break that up into two different numbers. So they won't just give you the mass of the solution, they'll give you the mass of the solute separate from the mass of the solvent. And it's a very common mistake that people make, which is that they will just use the solvent because it looks like the bigger number. So they'll just kind of use the solvent without getting the solute part. So you definitely want to make sure that you do that. So for example, if you had something that was 4.5% by mass sodium chloride, you can turn this sort of percentage into a usable conversion factor. And you could do that by basically assuming 100. And what that would really represent is, in this case, you had 4.50 grams of sodium chloride in 100 grams of solution. So that is a way, if you are given the percentage, you can actually kind of turn it into a conversion factor. Just because it is a conversion factor, you could also flip it around the other way, and you could put 100 grams of solution up on top is 4.5 grams of sodium chloride. So um, you could definitely use the formula and plug everything in, but sometimes you can take a more dimensional analysis approach and use the percentage as a conversion factor. And again, you could just assume 100 and basically keep the numbers the same. And in this case, because it's mass to mass, it is grams over grams, basically, is what we're using. So that's why we go with the 4.5 grams over 100 grams, gives us our percentage in that case. Let's take a look at one here. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. What is the mass percent of the solution? So take a moment or so and see what you come up with. We're looking for the percent mass to mass here. Okay, let's take a look. So we're looking for the percent mass to mass. So we can start with our formula here, which again is the mass of the solute divided by the mass of the solution times 100%. So in this particular case, we're given 2.5 grams of calcium chloride. That's going to be our solute, as that is the smaller mass there. So the mass of our solute here is going to be 2.5 grams. Water here is going to be our solvent in this case, and the mass of our solvent will be 50 grams. So we do have the mass of the solute. Remember again, the mass of the solution here is both the solute plus the solvent. So as you can see here, it is given to you separately. So to get the mass of the solution, you do need to add those together, and that's going to get you 52.5 grams. And that is what should go on the bottom again here, not 50, which is just the solvent by itself. And at this point, we could now plug everything in. Our percent mass to mass is going to be 2.5 divided by 52.5 times 100%. And that's going to give us 4.76. In terms of the units, really the grams kind of cancel out. So this is a percentage it's left as. Percent M/M is usually what you kind of give. And if you want, you can put what it was, which was calcium chloride in this case. Question on that calculation. So like I said before, it's really important, especially in these type of problems, because they very much will give you those numbers kind of separate from each other. You want to make sure you're not just using the solvent, that you do get the actual mass of the entire solution. Any questions on that there? Okay. All right, so why don't you try this one? Concentrated hydrochloric acid contains 37.2% by mass hydrochloric acid. What is the mass of hydrochloric acid in 35.5 grams of this solution? So take a moment there, see what you come up with. Okay, let's take a look. So again, obviously we're dealing with percent mass to mass, which we could use our formula here, our mass of our solute divided by the mass of the solution times 100%. Now, you could definitely kind of use the formula if you want. We are given in this case the percent mass to mass, which is 37.2%. We are also looking for the mass of the solute, and we have the mass of the solution given to us, which is our 35.5 grams. So we really do have this. We do have this. You could just rearrange this formula if you wanted to and solve for it. But if you maybe can't remember the formula, not sure how to rearrange it, or you're not sure, because they did give us sort of the percent mass to mass, we could take, again, a more kind of conversion dimensional analysis approach to it. And basically what that means is, again, you have 37.2 grams of hydrochloric acid and 100 grams of solution. And you can use this again as a conversion factor, 100 grams of solution, 37.2 grams of HCl. So you have the mass of the solution given to you. You could take your 35.5 grams of solution, you could put it over 1, and again, dimensional analysis, opposites cancel, so you could use it as a conversion factor like we see there. And we could put it in there, 37.2 grams of HCl and 100 grams of solution. Because this is dimensional analysis, as we've done a lot, we know we're multiplying the top, we're dividing the bottom. And just by taking sort of that approach, you don't have to worry about, did I correctly rearrange this equation for you? It basically just did it for you without maybe having to think too much about doing so. The grams of solution will cancel. And if we do that, we essentially take 35.5 times 37.2 divided by 100, going to give us 13.2 grams of HCl in this case. By the way, that is the exact same math you would do, obviously, if you did rearrange that equation. It would be basically the exact same math. So again, as we talked about many times, sometimes just taking a dimensional analysis approach is an easier way because all you have to think about is opposites cancel, and it will kind of rearrange formulas for you without necessarily maybe having to do it yourself. Any questions on that one there? Yeah. Yeah, so it's basically because what where it's given to us was a percentage. So usually when you want to kind of convert a percentage into like a conversion factor or kind of a usable number, you usually assume 100 of something. And the reason you do that, it just keeps the numbers the same because you got 37.2% on your exam. You got basically 37.2 points out of 100, right? So it keeps the numbers like the same. And that's why you can assume anything you want, but the numbers would change. And obviously, that would be more confusing. So that's why we always assume out of 100 grams of solution, because that just keeps everything the same number. Yeah. Yeah. How do you know you're going to be using this? Because in the problem, basically when it says something like this, like 37.2% by mass, that's basically mass percent. So that's basically where that number came from is from that calculation, which is the percent mass to mass. And that's basically what mass to mass means is basically how many grams of your solute is in that grams of solution. That's why it's mass to mass, grams over grams, basically. And that's why when we convert it into like a conversion factor, we take like 37.2 grams over 100 grams, and that's how we kind of get that conversion. Yes, sir. You don't. You could plug and chug into this equation if you want and rearrange it. It'll be the exact same math. It's just, you won't have grams there. You just have maybe percentages and stuff like that instead. Yeah. 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 As long as you have some units, yeah, and this is rearranged correctly, you'll come out the same. It should be okay. Yeah. Other questions? Okay. Now, in addition to mass percent, there are a couple other sort of percent concentrations that are commonly used for solutions. Another one is volume to volume percent, or percent volume to volume, and that is the volume of solute over the volume of solution times 100%. This is like what is used like in alcohol percent volume by alcohol, that type of stuff. So this is the percentage that's used there. This is essentially kind of like mass to mass percentage grams per grams. This is like milliliters per milliliters usually. So milliliters on top, milliliters on the bottom. It works really the same way. If you had a 4.5% by volume sodium chloride solution. Again, if you wanted to kind of turn that into a conversion factor to use, that would mean you have 4.50 milliliters of sodium chloride in 100 milliliters of solution. Or again, you could flip it around the other way and use it as a conversion factor in the other flipped way. in this particular case. Now, in this case, unlike the previous one, you oftentimes don't have to be super careful about the solution. They very often will just give you the volume of the solution, so they won't break this one up into like solute and solvent most of the time. So again, most of the time on this one, they'll just kind of straight up give you that volume of solution, unlike in sort of mass percent. So volume to volume percents, again, it basically compares the volume of the solute to the volume of solution times 100, while mass percent does grams of solute to grams of the solution times 100%. The last sort of percent by or percent concentration that's commonly used is what is sometimes referred to as percent mass to volume. And that is the mass of the solute divided by the volume of solution, also times 100%, if I can slip it in there. And this is basically almost like density is grams over milliliters, basically. So grams over the volume. And in this case, same idea. If you had a 4.5% mass to volume sodium chloride solution, that would mean you have 4.50 grams of sodium chloride and 100 milliliters of solution. Again, just assuming 100 to keep the numbers the same. And you can flip it around if you needed to. 100 milliliters of solution will give you basically 4.5 grams of sodium chloride. So once again here, kind of like a density sort of situation, grams per milliliter are the units here. And really for all these percent sort of concentrations, the ending units, if you're calculating the percentage, is usually just the percentage. And you could add the M/M or V/V or M/V in terms of it. Any questions on that one? Obviously, it works the same as the other. You just plug the numbers into the formula there, and that'll give you the percentage. So let's take a look at one here and see. What is the mass to volume percent of bromine in a solution prepared by dissolving 12 grams of bromine in enough carbon tetrachloride to make 250 milliliters of solution? Okay, let's take a look. So obviously here we are looking for percent mass to volume, and that's what the M/V means. And because that's percent mass to volume, we want to make sure we're using the right formula. And that would be the mass of the solute here divided by the volume of solution, again, times 100%. In this particular case, we have 12 grams of Br2. That is the mass of the solute. That is the smaller part of the solution, which is our 12 grams. We have carbon tetrachloride, so that is our solute. And in this case, the carbon tetrachloride is actually the solvent in this case. And we have enough solution here to make a volume of 250 milliliters in this case. That's actually everything we need to actually calculate it. All we have to do is just plug that in, and that would get us basically 12 grams divided by 250 milliliters times 100%. And that's going to give us 4.8%. And usually people will just do the percentage with a little M/V next to it. And that would be Br2 solution in this case. Yeah. Question on that calculation. This is also a really good example of a place where water would be a terrible solvent in this case. And that is because Br2, if you remember, is two of the same, which means that is a non-polar molecule. And that means that water, which is polar, is going to be a terrible solvent because, again, like dissolves like, they are not going to mix really well. That is why they needed, in this case, carbon tetrachloride, which if you quickly kind of sketch it, looks something like this without all the dots there. But that is a symmetrical geometry where everything on the outside is the same. That's going to be also a non-polar molecule. So here we're using a non-polar molecule like carbon tetrachloride to dissolve a non-polar substance like Br2, they're going to mix really well because they're going to be using the same type of forces that they use with themselves in this case. Water here is not going to work at all, would never let it dissolve. Basically, you'll have two different layers that would basically happen in that case. Any questions on that there? Yeah. All right, one last little percentage concentration here. Calculate the grams of KCl and how much water there is in 225 grams of an 8% KCl solution. So you got about 225 grams of solution. It's an 8% mass to mass potassium chloride. How many grams of that is potassium chloride and how many grams is water in this case? Obviously here, potassium chlorides are solute, waters are solvent in this case. So here we're doing percent mass to mass. So we can look at that equation here, which again is our mass of our solute, mass of the solution, and times about 100%. So in this particular case, we're looking for the grams of KCl, which is our solute. So we're looking for the mass of our solute. We're also looking for the mass of our water, which is our solvent as well. So we're looking for basically both of those. We are given the mass of the solution, which is 225 grams. A reminder that the mass of the solution is basically both of those guys added together in this case. So we got to at least get one of those numbers there, the solute or the solvent. And we can use the mass percent given to us. Again, we could plug it into the formula, or again, you could take more of a conversion factor sort of approach. And again, if you did a conversion factor approach, that means you have 8 grams of KCl and 100 grams of solution. Or again, you could flip it around the other way if you need to and use it with 100 grams of solution and 8 grams of KCl. In this case, we do have the mass of the solution. So if we just take that kind of dimensional analysis approach, we got 225 grams of our solution. We're going to use our conversion factor with solution in the opposite location, which is like so. Once again, dimensional analysis, multiply and divide, grams of solution cancel. That's going to yield us here 225. My calculator turns on maybe. 225 times 8 divided by 100. Looks like about 18 grams of KCl. That is the mass of our solute in this case, right? Now that we do have our mass of our solute, we know the mass of the solution, as I mentioned a second ago, is basically the mass of our solute plus the mass of our solvent, which is our water. We know that this is 225 grams equals 18 grams plus the mass of our solvent. We're going to subtract that to the other side, and that's going to give us that basically the grams of water, which is our solvent in this case, would be 225 minus 18, going to give us about 207 grams of water in this particular case, yeah, which again is our solvent, and 18 grams of our solute. Any question on that one? So again, basically kind of same calculation as earlier, except again, using the mass of the solution also allows you to figure out basically the mass of the solvent, in this case, water, goes here. In this case, water is a really good solvent because KCl is an ionic compound. Ionic compounds, positive, negative things work really well with water that is also positive, negative on one side and the other. So they interact really well with each other through surrounding those ions I think we talked about earlier on this semester, or in the chapter here. Any questions on percentage concentration? Yes. It is, yeah. So the solute, the smaller part of the solution, is basically the stuff that's dissolved in it. And it's really the name of the solution is always the solute. So this was a KCl solution. So KCl tells you the name, that's the name of the solution. That's always going to be the solute. So again, if you had like a calcium chloride solution, calcium chloride would be the solute. So whatever the name of the solution is basically the solute, and that's how you kind of could know that's maybe what you're looking for. Other questions? Yeah. You would have to use the equation that goes with percent mass to mass and just think about what was given to you. So even if you didn't want to do sort of this dimensional analysis approach, you could look at the equation and go, I was given this, I was given this. That's right here is the only thing I was not given, right? So that would make sense to start there, and that would give you the mass of the solute, and understanding that the solution is both the solute and the solvent together, then you can get the solvent from that because it already gave you the solution. So if you want to take, again, more of the formula approach, just think about what's given to you. And usually what's not given to you or what you're missing is usually a good place to start with. And just think about what you're solving for. Yeah. Other questions? All right. So as we've been talking about through this, again, you could always convert those percentages into conversion factors and use them, or you can plug right into those formulas and just rearrange and solve for what's missing, and that will kind of take you down the route of where you need. Let's then talk about probably the most common unit of concentration for solutions, and that is molarity. And molarity is really probably the unit of concentration that you see the most. It is abbreviated with a capital M, which stands for molarity, and it stands for the moles of solute per liter of solution. Although most people just call it basically molarity is moles divided by liters, basically. But that's really what the moles and the liters are for. Now, you could think of this really as like a formula, kind of like density's formula. You oftentimes may need to solve for any one of these three things, molarity, moles, or volume, or liters. So if you wanted liters, that would be moles divided by molarity. And if you wanted moles, which is a common sort of conversion, you got to take liters times molarity. So those are a few different ways that sort of formula is rearranged. These are the numbers you most commonly see in lab on your bottles that you use. Usually a number and a big M next to it. The bigger the number that it has an M next to it, the more concentrated and strong that is. So if you have like an 18 molar solution of hydrochloric acid, that's pretty darn strong. Yeah, there's a lot of hydrochloric acid in that solution rather than like a 0.01 molar hydrochloric acid solution. That's a more dilute solution along the way. What's up? Don't drink anything in lab is always a good advice. So just like the others though, and probably really important when you're doing calculations with molarity, if you have a 4.5 molar solution of sodium chloride, I would highly recommend that if you're going to use this molarity in a calculation, you get rid of the big M. And the reason for that is most people, when they try to do the calculation with just the big M there, they have no idea about that there's two units. There's moles and liters there. They have no idea about the liters part. They just think moles is ACM, and they forget all about the volume aspect of it. So to convert this really into probably a better way to do a calculation with this number, you would take the number and it would stay with the moles part, and it's always per 1 liter. So if you do it that way, you can at least see both of the units, and you should kind of write it like that as well, because in that dimensional analysis, top, bottom, so if you need to use it like dimensional analysis, opposites will cancel. But I can't tell you how many people's papers I've seen over the years where they try to do calculations with the big M and they have no idea there's even like a volume there. All they think about is, like I said, M moles. They have no idea about it. So it's a really good idea to like kind of get rid of that big M and insert both units. So at least visually you'll see both units and hopefully do something with the correct units and stuff like that. So how do we get to some of these numbers if we had to do some type of calculation? Well, a very common sort of conversion that you have to do with molarity is taking grams to moles, and we did a number of those. And a reminder, that is your molar mass from the periodic table. that you use to do that conversion. So very commonly you're given the grams of everything. You got to convert them into moles. So you go to the periodic table, add up all the molar mass like we did in the previous chapter, and convert those grams to moles. Also, a very common conversion that you also have to do with this is milliliters to liters. So like in the laboratory, very often you collect volume that's in milliliters, and you have to use liters in this formula here. So again, there are in 1 liter, 1,000 milliliters is also a very common conversion that's used in these problems. And you do want to definitely make sure that whenever you're doing, say, like this calculation here, and you're trying to figure out moles, for example, that the volume's always in liters when you times it by molarity. Otherwise, you actually don't get moles. You get what are known as millimoles if you take milliliters times it. And if you don't recognize that, you'll be off by like a factor of 1,000 on your answer and stuff like that. So you can take milliliters times molarity, but it gives you what's known as millimoles and not moles, which is most likely what you're probably looking for, which is moles. So you don't want to do that. So what does that mean? If we have, for example, a 1 molar solution of sodium chloride, that means basically we basically have 1 mole per liter of sodium chloride solution. Now, sometimes you may be interested in maybe not the whole ionic compound, because this is a sodium chloride, which is an ionic compound. It's a strong electrolyte, which means when it's in solution, it's really not staying together. You actually don't have any sodium chloride units together. You have basically 100% sodium ions floating around and chloride ions floating around. You have none of those sodium chloride units still together. So if you were looking at something like this, NaCl, and in solution, it's going to break apart into sodium ions and chloride ions. If you know the concentration of the whole thing here, which is 1 mole per liter, you can figure out the concentration of just the sodium ion or the chloride ion if you're interested in. And it's actually something kind of like what we've done before, which is like stoichiometry, like the mole to mole relationship. For every one of these, you get one of these. And basically how that relates to molarity is you take 1 times the molarity of the solution. And in this case, we would have 1 mole per liter of sodium ions, or that is basically 1 molar sodium ions. And when we look at the whole thing to just the chloride, it also is a 1-to-1 relationship, which means we would take 1 times the concentration of the whole thing. And that would give us that we have 1 mole per liter of chloride ions floating around that solution, which is also 1 molar. And you can write it as a big M if you want to. So sometimes you may be interested in maybe the ions that are floating around, what their concentration is. And you basically could relate how concentration works is you can relate it to how many ions you get per guy. So for example, if we had a 1 molar solution of calcium chloride, when calcium chloride breaks apart, we get a calcium ion, but we actually get 2 chloride ions when that breaks apart. So in solution, we're going to get 3 ions basically floating around in that solution. So for every one of those calcium chlorides that go for a swim, you're going to get a calcium ion and 2 chloride ions basically floating around in that solution. So if this guy's concentration was 1 molar, and we were interested in the concentration of the ions that are present, we could kind of do the same thing. For every 1 of the whole thing, we get 1 of the calcium ions. And how that affects concentration is take 1 times the molarity of the whole thing. And this solution would be 1 molar calcium ions floating around in there. But when we look at the chloride, it is a 1-to-2 relationship, which means you actually have to take the concentration of the whole thing and multiply it by 2. And this would be 2 molar chloride ions floating around there. So basically what this tells you is you have twice as many chloride ions float around that solution as you do calcium ions, right? For every one calcium, you get twice the amount of chloride floating there. And how their concentrations related is for every 1 molar of calcium, you get 2 molar or twice the concentration of chloride. It is not additive when you kind of look at ions by themselves. Obviously, if you take 2 and 1, it doesn't equal 1, but it's sort of like a relationship of how concentrated one ion is versus the other. So if it broke apart into a 1 to 3, you would take 3 times the concentration, 1 to 4, 4 times concentration, and so forth, if it broke apart in terms of the ions. So not too much in our class. We'd be maybe super interested in ions, but we'll look at the whole thing together. But that's how the relationship of concentration of an ionic compound, the whole thing relates to its ions. You basically multiply the concentration by however many ions you get. Yeah. It does. It can be any concentration. I just did 1 because it was an easy number. But, it's same thing if you had, say this was like 2.5 molar, right? This would again be a 1 to 1, and this would be 2.5 molar. If this was, say, 2.5 molar of the whole thing, this would be 2.5 molar into here. And this concentration would then be 5 molar, right, for that and stuff. So it doesn't matter what the concentration is, but that's how the molarity relates to the whole ionic compound to each of the ions. It's basically like a stoichiometry relationship, a mole to mole relationship. And again, however many ions it breaks into, that's what you want to multiply the whole concentration by. Yes. You don't. It's not additive. So if your question is, before I started scribbling again, we had 1 molar and 2 molar. That adds up obviously to 3 molar, which doesn't equal 1. So it's not additive like that. It's concentration is more like when you're doing it, looking at the ions, is more like sort of the relationship or proportion you have in there. So if you just look at the picture here, right, for every 1 of the whole thing, you're just going to get 1 calcium ion floating around, but you will get 2 chloride ions floating around. So if you just think about that way, you got twice the amount, right, of chloride than you do calcium. And that is the relationship we actually see in terms of the ions. There's twice the concentration of chloride floating around because you get like a 2-for-1 deal on that, right? So you get 2 for every 1 that goes in, and that's the relationship in terms of concentration. But it's definitely not additive like it adds that. Yeah. Correct. Yeah. So this is typically the only place that you would do it is, and again, sometimes you are interested in just maybe the ion by itself, not the whole thing. And you need a way to kind of relate the concentration of the whole thing to the ions that are floating around the solution. And that's sort of how you do it, is sort of that kind of like mole to mole relationship is really what it is. Yeah. Other questions? Okay. All right. So let's take a look at a problem here and see. Calculate the molarity of a solution that you prepare by dissolving 0.6 grams of KBr in enough water to make 1.25 liters of solution. Some numbers that will be helpful. Potassium is 3910 on the periodic table. And bromine. Bromine is 7990 on the periodic table. So we're looking for the molarity, or moles per liter here now. Look, obviously we're looking for moles per liter. So we want to think about, do we have anything given to us? And we do have the volume of solution. It's already in liters. Again, commonly you sometimes do need to convert milliliters into liters, but that's already done for us. So we actually have the bottom part here that we need. So we need the top part, which is moles, and that's what the other piece of information is going to allow us to do. We know we have 15 grams of KBr, which, by the way, is our solute in this case. Water, again, here's our solvent in the solution. So as I mentioned a second ago, very common as well, in addition to like milliliters to liters conversion, is grams to moles conversion. So again, that is using the molar mass from the periodic table. So we would go to the periodic table and find that K and the Br. In this case, we just need to add it together, and that will give us really our conversion factor to use to convert our grams into moles, which is 119 grams per mole. Remember, it's really just a conversion factor to change units. So still going opposites cancel, grams are on top. So we do need to flip this to the bottom and put the grams on the bottom and the moles up on top. And again, we're still multiplying and dividing here. Grams are going to cancel. And that's going to then convert our grams into moles. So we'll go 15.6 divided by 119. We'll go 0.131 moles of KBr. That is the top part of what we need here. So now that we have the top and the bottom, all we have to do is put it together. We're going to go 0.131 moles divided by 1.25 liters. And that's going to get us 0.131 divided by 1.25. That's going to give us 0.105. Now, the units here actually do not cancel, so you could leave your answer in one of two ways. Again, the number always goes with the moles, and it's always per 1 liter, so you could leave it like that. At this point, you could, if you wanted to, convert the moles per liter back into the big M and leave it as a big M as your answer. And you could also put KBR next to it as well, since it's KBR. So you can leave it either way. But again, here the units will not cancel. So that is the units of molarity, moles on top, liters on the bottom. Any questions on that? Yeah. Yeah, so if you, in terms of the answer, you could leave it like that if you like. Big M, and I just ran out of room, but usually put the KBR to the right of it. But yeah, other questions? All right, so these are just some chemistry units that we've talked about here. And let's take a look at another example here. What is the mass of sodium nitrate in grams that's needed to make a 2.5 liter solution that is 0.15 molar sodium nitrate? Again, some numbers here. Sodium 2299, nitrogen 1401, and oxygen 16 from the periodic table. For the grams of sodium nitrate, we do have a volume given to us, 2.5 liters. We also have a molarity given to us, 0.150. So clearly molarity is involved. So if you're not sure where you maybe should begin, you could just think about the molarity formula, right? Which is basically moles per liter. So in this case, we do have liters given to us. We do have the molarity given to us. So logic again would tell us that perhaps the only thing we don't have is moles. And that's a really good thing to maybe get, because if we have moles, we know we could go from moles to grams using the molar mass, like we went grams to moles using the molar mass, right? So that's sort of our process here. We want to use this to get to moles. We then want to use our molar mass from the periodic table to take those moles to grams. So again, if you're not sure where to start and you know some type of formula, think about what's given to you, and you can sort of just probably solve for what's missing. And again, that's a good place to start. Once again, as I mentioned before, when we're using molarity in a calculation, it again is a really good idea to kind of think of it like a conversion factor. And what that basically means is we have 0.150 moles per liter. You could, if you needed to, flip it around like a normal conversion factor, and you could use it in that orientation. So if we were going to solve for moles here, we would multiply the liters to the other side, and you would get liters times molarity. Or if you don't even want to, again, mess with that, you again could take the kind of dimensional analysis approach, which means I got liters, so that's a good thing to start with. And again, opposites cancel, which means I need liters on the bottom, so I definitely want to use it in this direction. And now I don't really have to worry about sort of the formula there. I am kind of doing the rearrangement by just kind of taking this sort of approach to it. The liters will cancel, and that will give us our moles, in this case, of sodium nitrate, which is 2.5 times 0.15, and that's going to give us 0.375 moles of sodium nitrate in this case. That, by the way, is pretty much the exact calculation here by rearranging the equation. Any questions on that so far? So at this point, we're in moles, which is close to what we want, but we do want grams. So just like taking grams to moles is the molar mass, if you're going backwards, it is still the molar mass from the periodic table. That's your conversion factor to do that. Remember, when we do have something like sodium nitrate here, we're just going to add up all the parts to it. So we do have one sodium at 2299. We do have one nitrogen at 1401. And we do have, in this case, 3 of the oxygens. Let's go below 3 times 16 grams per mole. Adding all that together, I think it's an even 85, if I'm not mistaken there, grams per mole. Remember that this molar mass is really also just a conversion factor. And again, we're going to use it to go, in this case, from moles back to grams. So taking our number from the previous step there, 0.375 moles of sodium nitrate. Once again, moles are up on top. So when I use my molar mass as a conversion factor, I do need the moles on the bottom, opposite location, to cancel, right? Again, still multiplying and dividing here. Moles are going to cancel. And that's going to get us here an 85, I think. Call it, I'll go up on top here, 31.9 grams of sodium nitrate in this case. Yeah. Any questions on that one there? So basically what this calculation means is if you weighed out 31.9 grams of sodium nitrate and you put it in some water and dissolved it and enough water to get to 2.5 liters, gave it a good mixy, shaky, you would be ending up with a solution that has this molarity basically made, is basically what those numbers basically represent. Any questions on molarity here? Let's get that one, I think. The next thing we're going to talk about is actually dilution. And dilution is the process where we really add, in a lot of cases, more water, but it's technically your solvent. And since water is a very common solvent, it is a process where we take a more concentrated solution and add something like water or more solvent to it to lower its concentration to become more dilute. The reason this works is if you think about what molarity really is, molarity again is moles of solute over liters of solution. And since a solution, as we've been talking about, is both the solute plus the solvent, when you do a dilution and you add more solvent or water to it, you're increasing this number, which is increasing the bottom number. And that means that you're going to have a small number divided by a larger number. That's going to give you a small number when you do that division. And what will end up happening is as you add that water, the molarity of your solution will come down because you're basically diluting it. So I maybe did an example there before spring break, right? You get like a big gulp drink, right? And it's got a bunch of ice in it, and you leave it in your car, you come back, it melts. All that ice is now water that's been added to your soda or drink. It doesn't taste as fresh as it did before, right? Because it's now majorly diluted. It's not as concentrated as it was when you first got it. And that's what happens with a dilution. So the only thing that basically changes is the amount of solvent or the volume of solution. The moles that you have of solute before the dilution and after the dilution is exactly the same. You basically just watered it down if you want to think about it that way in terms of the dilution process. That is usually the process that's used to convert really concentrated solutions into more dilute solutions that you use in the lab. Here's one way you could do that. It's a volumetric flask. Add a little water, add your more concentrated solution to it, top it off with some water. Volumetric means expensive. You shouldn't break these things. They usually have one marking on it, and that one marking represents the volume of the flask in this case. And you fill it to the top there and you mix it up. You now have a diluted solution that's been diluted down, obviously, with a bunch of water. Now, there is a formula that's used in the calculation of a dilution, and I would say most people roll with M1 V1 equals M2 V2. This is usually before the dilution. That is your molarity and that is your volume. This is usually after you do the dilution. And again, that's the molarity after the dilution and the total volume after the dilution as well. The reason why most people use M1 V1 equals M2 V2 is because molarity is the most common unit of concentration. but books and stuff do roll with C1V1 equals C2V2. C here is just generic for concentration. Although molarity is the most common unit, you could do this with any unit of concentration. You could do this formula with like mass percent on both sides, volume percent on both sides. But again, most people kind of use molarity as usually the most common unit, and that is what is typically used. Now, when you do this equation here, especially if you're using sort of this version, earlier we talked about molarity and volume. And when we said if you're using molarity by itself and you want moles, your volume does need to be in liters for everything to work out correctly. The one exception is if you use this equation, you can leave your volume in milliliters and it will work out okay. And the reason it works out okay, for example, let's just say that I was solving for M2. M2 would be M1 V1 over V2. And if we just look at units, molarity, if I left my volume for V1 as milliliters and my volume for V2 as milliliters, they will divide out and you'll be back to molarity. So it'll work okay. So if you're specifically using this dilution equation, you technically don't have to convert your volume to liters. You can if you want, but you don't have to. And it will work out fine with molarity if you leave it in milliliters. If you're solving for a volume and you leave the volume, other volume in milliliters, and let's just say you were solving for V2, which would be M1 V1 over M2. We just look at units, molarity times milliliters divided by molarity. Molarities will cancel. You'll just end up with milliliters in this case. So if you want to, you could convert all the volumes to liters when you're using this equation, or you could leave them in milliliters and it will come out okay and it'll be okay at the end. Just in the end, you will get milliliters if you did volume. If you're doing molarity by itself, like this calculation, and it is not involving a dilution or that formula, you 100% of the time should convert it to liters. Otherwise, you will most likely get the wrong answer. So if you want to be safe, just convert it to liters all the time. You'll be fine. But technically speaking, you can leave it in milliliters in this case, and you will be in okay shape. Any questions on that there? So just to look at one here to finish up together, what is the volume of 19 molar sodium hydroxide that is needed to prepare 1 liter of 0.15 molar sodium hydroxide? So this is a dilution problem. I know this because I'm starting with sodium hydroxide. I'm ending with sodium hydroxide. I'm not making anything new here. The only difference is the concentrations are different. So this is definitely a dilution situation. M1 V1 equals M2 V2. So what is essentially happening here is you have a bottle sitting there of 19 molar sodium hydroxide, and you want to make a new container that has a volume of 1 liter, or we'll call it 1,000 milliliters, which is the same thing, and it has a molarity of 0.15 molar. So this is really the situation of what you're trying to do here. And you could call either one of these ones or twos, but most people take the more concentrated one as the one, so that would be M1. This would be M2 and V2. And in this particular case, we could solve for then V1. And we're going to divide this to the other side. And that will give us that V1 is equal to M2 V2 divided by M1. Putting in our numbers here, we end up with 0.15, bless you, molar. And I'm going to actually use the milliliters in this case, just so I get a little bigger numbers. And that's 1,000 milliliters, which is 1 liter, divided by 19 molar. The molarities will cancel, and again, because I did it in milliliters, I'll end up with 0.15 times 1,000 divided by 19, and that's going to get me roughly 7.9 milliliters. Again, if I did it in liters, it will look very similar, except obviously I would end up in liters if I did that. So 1 liter divided by 19 molar. And here I would end up with 0.0079 liters. So if you did it in liters, you end up in liters. If you converted it to milliliters, you'll end up in milliliters. They're both the same. If you times the top guy by 1,000, you get the bottom guy, which is 7.9 here. What does that 7.9 really represent? That is how much of the more concentrated solution you would go in and take out and put into your new container. So when you solve for V1, you're basically saying I need to put in there 7.9 milliliters of my more concentrated sodium hydroxide solution. Now, in order to finish this problem, right, and make this solution, can I just put 1,000 milliliters of water in there with it? I cannot, because if I did that, I would have 1,000 plus 7.9. That's 1,007.9 milliliters. That's too much volume. My molarity will not be correct. So because I've already put 7.9 milliliters of the more concentrated solution in there, I can figure out the volume of water that's needed by taking basically V2 minus V1. V2 is my final volume I'm looking for, which is 1,000 milliliters, minus my 7.9 milliliters that I've already put in there. And again, 1,000 milliliters is 1 liter. And if I do that, that tells me I need to throw in there about 992.1 milliliters of water with it. So I would top in there 992.1 milliliters of water. When I do so, that gives me a total volume of 1,000 milliliters, which is what I'm looking for. And at this point, I could actually give it a little mixy, shaky. And what I should have at that point is now a solution that has a molarity of 0.15 molar. And I say this because a lot of dilution problems will very often ask you that question, not necessarily about the dilution, but it'll ask you like how you're going to make the solution, or it'll ask you how much water you need to add. So a very easy way that you can kind of usually calculate the amount of water you need to add to do the dilution is take V2 minus V1, final volume minus the initial volume of what you're adding, and that usually will give you how much of the solvent or water you need to add. Any questions on that there? Yeah. Yeah, so in this particular case, it didn't really specify, so you could actually give the answer in liters or milliliters. The actual answer to this question is basically these guys, and that again is how much of the sodium hydroxide you're taking from the more concentrated solution in this case, yeah.